So, we are discussing about the software controlled serial data transmission. So, in that we have discussed about the serial data transmission. So, we can write the program for serial data transmission. So, because we have to send ASCII 49H, means you have to send 49 is 0, 1 0 0, 1 0 0 1, and one start bit will be here 0, 2 stop bit will be 1 1. These are 2 stop bits. This is one start bit. This is the flow that we have to give. First you have to send 0, then you have to send 1, then you have to send 0, so on up to this one. Total this one is ASCII character 49. So, how to write the program for this? So, we have connected this microprocessor to port ASA. This is the serial data pin. So, inside this 8255 we have this serial data pin. I will connect to the port A, output port. Port A of 8255, I will program this as output port. Say PA naught. This is microprocessor. So, I have to send in this manner. First you have to send a stop bit, then 0. So, I will take this into some 16 bit register. So, I will take this 16 bit register, say AX. So, first bit is start bit, this is 0. Then character bits are, the first bit will be 0 in this direction, then 1, then 0, 0, then 1, 0, 0, then we have 1, this is character, this is start bit and this is character, then we have 2 stop bits 1 1. So, I want to take into AX is 16 bit register, total we have 11 bits only, remaining 5 I will take as do not cares. I will assume that 0 0 zeros. I will take the remaining bits as 0 0 0 0 0. Up to here this is character. Sorry, up to here this is character. These two are start bits. This is character. (49H). This is start bit and these two are stop bits. So, what is the hexadecimal equivalent of this one? This is 0 0 0 0 is 0 and then 0 1 1 1 is 7 and this one is 2 and this one is 4. 0724H. So, first I have to program this port output port A as output port. So, let us the address of this one is FCH, then control register will be FFH. I have to first program the port A as output port. So, to program all the ports as output ports, we know that ATH is the control register, we will out on to FFH, which is the address of the control load register, comma AL. With these two instructions, this will program all the ports of 8255 in mode 0 as output ports. Now, I have to send one by one total 11 bits. So, I will take this counter Cx with 11 bits 000B, the equivalent the hexadecimal equivalent of 11 will be B. Then because I have to send on PA naught, in AX I will take the total, the character start stop bits and the remaining bits of zeros. So, this will be 0724H, 0724H. So, in this we have to send the least significant 11 bits. The most significant by 5 bits we will not send, they are don't cares, we will stop after the 11th bit is transmitted. Okay. So, for that, so I am going to send only AL contents only. So, each time I will shift this. So, out FCH comma AL. So, what happens, this 0 will be outputted on PA naught. So, this will be outputted on PA naught. So, this 0, this PA naught, if I take this PA naught waveform, this will be initially without any transmission, this will be a mark. I have started here. So, this 0, this is the point. Then what you have to do is, we call a delay equivalent to 0.83 milliseconds in case of 1200 baud rate. So, this 0 will be there for 0.83 milliseconds. Then what I will do is rotate AX to the right by 1 bit position. Now, what happens here? This 0 will come here after the rotation, that is the first bit of the character. Then I will decrement Cx because I have already transmitted 1 bit. So, for that loop up. So, in this loop Cx will be decremented until Cx is equal to 0, this will branch to the address with the label of up. So, where should be this up now? Up should be out FCH comma AL. Now, what happens? Second bit 0 will be transmitted, this is 0 for 0.83 milliseconds because here delay is there again another shift. So, this 0 will comes to the LSB position. So, then this 1 will comes to the LSB position, this 1 will be transmitted for 0.83 seconds. So, like that this sequence will be outputted. Once all the 11 bits has been outputted, this will come out of the loop, simply have to halt. This is how using the software we can transmit any character with a specified number of start bit and stop bits. Similarly, at the receiver, this is about this serial data transmission. So, what about the serial data reception? So, what will be the block diagram? So, we have to program the port as input port. In case of transmission, you are programming the port as output port. Now, you have to program same port A only input port. So, whatever the data that is coming from this input port, you have to take into any register. We have to take on to D7 first, D6, D5, D4, D3, D2, D1, D0. This is register inside the microprocessor. I will write the program for this also. This is microprocessor. Then the microprocessor will generate the address correspond to this input port. So, like in previous program, we assumed that the port A address is FCH. that FCH or whatever the address will be generated by using this address decoder. This will connect to chip select of this signal. This is address decoder. AD stands for address decoder. So, this is going to decide the address of the port A and port B, port C, whatever the logic inside this. So, I am assuming that the address of port A is FCH, then port B will be the next address, port C will be next address, and control load register will be next address. So, the corresponding circuit will be present in this block, AD block, that will connect output of that AD block will be connected to chip select signal. Then because you are reading, so the microprocessor sends read bar signal. In case of transmit, write bar signal, and this logic is same regardless of whether this is a transmission or a reception. Okay. And here this has to be programmed as input port in reception, output port in case of data transmission. Now, the characters will be received here. So, what will the waveform here received will be, the first bit will be start bit 0, then 1, 0, 1, 0, 0, 1, 0, 0, 1, then 1, 1. So, this is start bit. First start bit will be received, then the character will be received. Character is, this is 4 and 9 character, then 2 stop bits will be received. So, whatever the data that is received on input line of port A, I will take into some register. Okay. Say let us take, I want to take this value into register AL or BL. So, what will be the program software for this? So, the first two instructions are same, move AL comma ATH. Sorry, here we have to program this port A as input port. Port A, in order to program the port A as input port, what is the control register? This is port C lower, we are not using, so we can take as output port. This is port B, we are not using, I will take as output port. This is mode selection for port B, I will take mode 0. This is port C upper, we are not using, I will take as output port. This is port A, port A I have to program as input port 1. Next, mode selection for port A, I will want to operate in mode 0 only, 0 0, and this is for IO mode 1. So, this will be 9 0. We have to take AL with 90H, so that port A will be programmed as input port. Out, control register is FFH comma AL. So, these two instructions will program port A as input port, port B, port C as output ports, all in mode 0. Okay. Now, I will make this counter to 8 now, because I have to store only 8 useful bits. I will take BL as 0 0, later I am going to use this BL contents 0 0 H. These are some initializations. Then first I will take the input bit in AL comma FCH. So, what happens, this is FCH port address. So, the first bit that is received, if it is a correct received character, then first bit should be 0, that will be available here. Okay. If I take in AL, in LSB it is available. So, I want to check whether this LSB is 0 or 1. Okay. For that, I will AND AL with 0 1 H, so that the last bit becomes whatever this the received bit, whereas the remaining bit becomes 0. Okay. So, whatever is received on input port, this entire input port, because we are not using PA 7 to PA 1, PA 6, PA 5, PA 4, PA 3, PA PA2, PA1, PA0. Here some bits will be received, but we are not using these bits. So, if I write in PL in AL comma FCH, this entire data will comes into AL register. So, what is interested is because this bits will be received on PA0. So, that is why I am ending this one. So, that this bit, if this is 0, it remains 0 only, if this is 1, it remains 1 only, the remaining all bits becomes 0. So, this is the bit that I want to read. So, that is why I have ANDed this AL contents with 0 1 H. Now, I will OR this because in BL I have taken 0 0 H already. So, I want to store finally this received character onto the BL register. Okay. So, but the first bit will be the start bit. So, until the start bit is 0, I have to wait, because if start bit is not 0, that is not the valid character. Okay. So, that is why what I have to do is, after ending with this one, jump on carry here itself. So, first bit, if the first bit is, so I have shifted this bit to the carry flag in ROR. Sorry, this is after this we have to write ROR AL comma 0 1 H. So, that the last bit, which is the bit that is received on PA0, will transfer to the carry flag. If this is 0, then this will be false, means that is a 0 bit. Otherwise, if this is 1, means this is not the valid character. I will wait until this the last bit, which is the first received bit, will be 0. This is an infinite loop. So, this will come out of the loop whenever the last bit is 0, that is start bit is 0. If start bit is 0, then it will come out of the loop. Then it is not enough actually, the start bit has to be 0 for 0.83 seconds. So, what I will do is I will call delay of 0.83 seconds. After that again I will check jump on carry here. So, if it is not 0, jump on carry, if this is true, means not 0, 1 means it is not a valid character. So, I will wait here itself. So, until a 0 has to be available for 0.83 milliseconds, till that time I will wait. Once this is coming out of this loop means, so the first bit is 0 and this is of duration logic 0, it is of duration 0.83 milliseconds, then it will come out of the loop. Then I will check for the first bit of the character. Otherwise, this will wait here until a valid start bit is received, this will wait in the loop. Once this is coming out of the loop means a valid start bit has been received. Now, I have to check for character bits. So, first character bit again I will write in AL comma FCH, because I have already called the delay. Okay. So, the second bit that should be received will be this. This I have kept this for 0.83 milliseconds. So, after that the bit received will be the next bit, which is the first bit of the character. So, that I will end with 0 1 H. So, that last bit remains whatever the received bit. If received bit is 0, the last bit becomes 0 because we are ending. If received bit is 1, the last bit is 1 because the last bit of this 0 1 will be 1. Okay. This I am going to OR with BL and I will store the result in BL itself. So, in BL initially 0 was there, all 0 bits, 0 0 0 0 0 0 0 0 initially. In AL we have the remaining all bits are 0 except for that these 3 bits are 0, because I have make this ending operation with 0 1 H. So, this 7 bit, the first 7 bit becomes 0. This bit will be whatever the received bit. Received bit can be either 0 or 1. If this is 0, if I OR these two, OR operation, then this BL will be having, after this the contents of BL becomes, the first 7 bits will be 0 0 0. I will not consider that. This bit will be whatever the bit of this one will be transferred. So, 0 if you OR with 0, 0 only. If this is 1, 1 if you OR with 1, this will be 1. So, simply the last bit of BL becomes the first received bit. So, in our present case this is 0. So, the first bit received will be here 0. Okay. Then I will call delay. Before that I will rotate, I will call delay, because this has to be present for delay of 0.3 milliseconds. Then I will decrement C by 1, because I have already stored the first bit. So, loop up, Cx will be decremented by 1. So, Cx becomes 7. So, this is not 0. So, it will go to up. Where should be this up now? The second bit received has to be checked now. So, loop up means this should be here. So, again I will input the data that is received here into AL. In that also we are interested in only last bit only. So, we will end with this last bit, and then we will OR with BL. But before this, what you have to do is, you have to rotate BL by 0 1 H, 0 1 H. Because this first bit that is received in BL I have to transfer here, so that I can store here the next bit that is received. So, we have to put this rotate operation in loop. So, what happens, the next second bit received will be comes here. Again you have to perform rotate operation, so that the first bit will move to the third position, second bit will move to the second position. Now, the last bit position will be free, which is used to receive the next bit. So, like that this loop will repeats. At the end of this loop, BL will contain the ASCII character that is received. So, at the end of this loop, BL will contain that 0 1 0 0, which is 4 1 0 0 1, because the first bit received will be 0. This will be rotated 8 times, because this rotate operation is in a loop. So, this will come here, second bit received will be here. So, like that this is 49H will be placed in VL. So, this is valid if received bit is valid, if it follows 2 stop bits. So, how to check now for stop bits? This program is for checking the start bit, and from here to here to receive the character bits, Now, we have to write for checking the stop bits, then only it is a valid character. So, again I will input in AL comma, because every time you are calling this 0.83 second delay. So, after the 8th character also 0.83 delay, then I have to check in AL comma port C FCH. Then jump on not carry now, because stop bit should be 1. If it is not 1 0, this not carry will be true. So, this will be, you have to jump not carry, you have to go to here. So, the thing is here, first bit is start bit you have received as 0, and the remaining 7 bits you have received as it is. After that, if this bit is not 1, means this entire character is false. So, again I have to start from this point onwards. That is why this here should be this here. Once if this bit is 1, it will come out of the loop, means first start bit is 1. Start bit is 1. Then I have to call a delay. called delay. Then you have to check for second start bit also. Again in AL comma FCH, same logic. Jump not carry means second start bit is not 1. So, in that case also I will go to again starting of this logic here itself. So, again I will start from start bit onwards, because that is not the valid character. If second start bit is also 1 after a delay also, jump not character not carry, jump not carry here. If both the bits are ones and they are available for 0.83 second 0.83 millisecond duration, then so we will confirm that the received character is valid one, then we will simply halt. This is about this serial data reception program. So, you have considered serial data transmission as well as serial data reception, and we can write the software programs to send the data as well as to receive the data. Okay. So, this is about this software controlled serial data communication. Now, the drawback of serial data software based serial data communication is sometimes it may become slower, okay, as I have discussed in case of 8237 DMA controller also. So, why the DMA controller is required? Normally this data transfer will take place through program instructions, but in some applications if the peripherals are fast like hard disk, so that much rate, the fast rate, the microprocessor cannot write the programs to receive the data at that fast rate. So, we have to go for the dedicated hardware. Similarly, here also, so in order to accept the data at faster rates, so instead of using the software programs, because here the software program we have to fetch the software program, we have to execute, this will take time. So, instead of that, if you have a dedicated processor, dedicated interface device, then that can perform these operations transmission and reception at the faster rates. So, the second approach is instead of software controlled serial data communication, we have hardware controlled serial data communication. So, the hardware dedicated device which is used to control serial data communication is called programmable communication interface. PCI, the IC number is 8251. This also can be called as, another name for this one is USART, universal synchronous asynchronous receiver transmitter. So, U S A R T, USART. Here, as the name implies, we are going to discuss both the types of synchronous data transmission as well as asynchronous data transmission. We know what is the difference between the synchronous transmission and asynchronous data transmission. So, this peripheral device 8251 is capable of performing both types of the data transfer, synchronous data transfer as well as asynchronous data transfer. There is one more this just advanced version of this 8251 is 8251A. Of course, this is compatible with 8251. Okay. So, I will just write 8251 only, it means it is 8251A also. Okay. Now, coming for this 8251A or 8251, this is a 28 pin IC So, to control this synchronous as well as asynchronous operations, totally it has 5 sections of blocks. So, it will be having one block is called address buffer block, then it will be having read write control logic. Normally in most of the peripherals these two logics will be common, read write control logic. Then it has a modem control, so we know that. So, in case of transmission of the data, digital data over telephone lines, we require modem. So, this will have some modem control signals. Then we have transmitter control, receiver control. These are some important blocks of this 8251, and we have some serial to parallel converter and parallel to serial converter normally. So, in case of software controlled, you have to use serial to parallel and parallel to serial conversion using the program, whereas here we will have a hardware. As I have told, this serial to parallel and parallel to serial conversion can be implemented by using shift registers. Okay. Now, coming for the block diagram of 8251 or 8251A, there will be some internal data bus like all other peripherals. This is internal data bus. Which communicates between the various blocks of this peripheral. As I have told, the different blocks are, the first block is data bus buffer. This is data bus buffer. This is a bidirectional, because data is bidirectional operation, data flow. We will be having 8 data lines. This 8251 is having 8-bit data lines. D7 to D0. Out of 28 pins, 8 pins are data lines. Then we have read write control logic. This is also bidirectional. Control signals are, some control signals are input signals, some are output signals, because it can read or write memory as well as IO. Then what are the different signals? The very first signal for this any read write control signals will be chip select bar. So, you have to first of all select this chip using some address decoding logic. Okay. And as the name implies read write, so we have read bar signal, active low signal, write bar active low signal, and the various control signals are, we have reset signal, then we have clock, then we have C by D bar signal. So, I will explain what is meant by this C by D bar signal, and this is chip select signal. So, totally we have 6 different signals for this particular block. And then the other block that I have discussed is modem control. So, for modem control we have 4 active low signals. Two are input signals and 2 are output signals. One is data set ready. I will explain the functions of all the signals in detail. data terminal ready. Clear to send, ready to send. So, you have the different 3 blocks here, this side. The other side we have parallel to serial converter, which will act as transmitter buffer, which is basically a parallel to serial converter. So, it will take the parallel data, it will convert serial, and there is one serial data signal which is called as transmit data, TXD. TXD stands for transmit data. Then we have transmitter control signals. We have 3 control signals correspond to the transmitter. One is transmit ready. Whenever the transmitter is ready, it will inform the device through a signal transmit ready, TX or DY, transmitter ready. If transmitter is empty, this will indicate through another signal called transmit empty. Then this transmitter will be having some clock, this is transmitter clock. This is going to decide the rate of transmission. This is active low signal. Then we have receiver buffer. Basically, this is serial to parallel converter. So, this will receive the data on a signal called RxD. This is reverse to that of TXD. So, the serial data will be received, this will be converted into parallel, that will be given to the internal bus of this peripheral. Similarly, we have receiver control. Here also there are 3 signals receiver control. So, we have this signals from here, here, and there will be connection between these 2. The signals of this one is receiver ready, similar transmitter ready, and then receive clock, which is active low signal. Instead of transmitter empty, there is one signal called here sync signal, which is synchronous signal. So, this synchronous pulses are required in case of a synchronous data transmission. Okay. This can be also called break character. So, these are the different signals of 8251 architectural diagram. So, total how many signals? These are 8 signals, 8, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and one ground and another is VCC. So, total 28 signals. Okay. Now, coming for the functions of each signal. So, chip select signal is obvious, the operation of chip select is, so whenever the chip is selected, in order to select this chip, CS bar should be 0. Okay. So, read bar, write bar signal, I will come to this read bar, write bar in connection with C by D bar. So, these 3 are related, these 3 signals are related, I will come to that later. Reset, whenever this 8251 receives a reset signal, 8251 will enter into the idle state. Whenever reset is 1, the 8251 enters into idle state. And because this inside this we have the sequential logic. So, it requires some clock to operate this all functions at a some rate. One important point here is this clock is nowhere related to the transmitter and receiver speeds. This is only this internal to this particular blocks only, internal blocks of this. This clock is not going to decide the speed of transmission and reception. The speed of transmission and reception will be decided by two clocks called receiver clock and transmitter clock. Okay. Now, coming for this read by write bar and see by D bar. If we go into some more details of this read bar, write bar, see by D bar, this is internal data bus. So, I am going to draw that detailed diagram of this C by D bar controller logic. This is somewhat data buffer, data bus buffer. Then we have read write control logic. There are two registers called, one is control word register, another is status register. This is read write control logic. The remaining signals I am not going to discuss here. I am going to discuss only three signals: read bar, write bar and see by D bar. So, this will go here, here or here. It will be decided by these three signals. So, this is one is called as control word register. And this is status word register. This is 8 bit, whereas this is 16 bit. So, the microprocessor will write some data into controller register. So, the direction will be here from control word register to internal data bus, whereas the microprocessor can read the status of 8251. So, that the direction will be like this. So, as the name implies, in case of control word register, because it is going to write bar is 0 here. So, when write bar is 0, here also you can read write data. So, if write bar is 0, whether this control read write control logic will refer to data bus or control word register, that will be decided by C by D bar. So, if this is data, C by D bar is equal to 1 and write bar is equal to 1, means data buffer will be selected. If C by D bar is 0 and write bar is equal to 1, control word register will be selected. Is it clear now? So, C by D bar is going to decide whether the control word register or data bus buffer is selected, even if you select the write bar as equal to 0. Similarly, read bar is equal to 0. So, we can read something, either you can read from the status register or you can read from the data bus also. Here also read bar can be 0. Now, when read bar is equal to 0, whether the microprocessor is going to read from the data bus buffer or status word register, that will be again decided by C by D bar. If C by D bar is equal to 1 and RD bar is equal to 0, this refers to status word register. If C by D bar is equal to 0, RD bar is equal to 0, it refers to data bus buffer. This is about the functions of read bar, write bar and C by D bar signals. Now, what about this 16 bit control word register and status word register? What are the formats of this control word register, status word register? So, like in case of other peripheral devices, we have some format which is going to decide the modes of operations and the various details of this transmitter as well as receiver. Now, what are the formats of this control word register and status word register? Control word register is 16 bit, but again this will be independently divided into two 8 bit registers. One is called mode word register, another is called command word register. Each is 8 bits. So, what is the format of these two registers? First I will take mode word register. So, the format is this is 8 bit register. The last 2 bits LSB 2 bits are this is D0 D1. These 2 bits are called as baud rate factor. This is going to decide baud rate factor. We know what is baud rate. If this is 0 0, this is bit configuration 0 0, the operation and bits, bit combinations. 0 0 means synchronous operation. As I have told, 8251 can operate as either synchronous mode or asynchronous mode. Okay. So, if this is 0 0, this is synchronous operation. If this is 0 1, then this is asynchronous operation, async, and the baud rate factor is 1. Whatever the baud rate we have set, that way is to be multiplied 1 means that will be taken as it is. Okay. I will explain this what is meant by this baud rate factor 1, 16 and all. So, we will discussing about some few examples. 1 0 asynchronous, but baud rate factor is 16. 1 1 asynchronous only, baud rate factor is 64. For only 0 0, the 8251 will operate in synchronous serial transmission mode, whereas for the remaining 3 combination asynchronous. In one case direct baud rate is taken, and in the other cases, in one case it is a 16 factor is taken, in other case 64 factor will be taken. That is about the last 2 bits. The next 2 bits are character length. D2, D3 will decide the character length. In case of ASCII, character length is 8. Even though it is a 7 bit code, but we are going to use 8 bits. This is going to decide here. This is 0 0, character length is 5 bits. 0 1, character length is 6 bits. 1 0, character length is 7 bits. 1 1, character length is 8 bits. So, we can have the character length from 5 to 8 range. We can have character length of 5, 6, 7 and 8. The next 2 bits D4 and D5 are parity control signal. This will be parity control. As I have discussed in the earlier lecture, we have to send some parity signals in order to detect and correct the errors at the receiver. Okay. We can transmit either even parity or odd parity, or we can have no parity also. For short distance communications, even without parity also you can send. So, that will be decided by these 2 bits. This is 0 0, no parity. In fact, x 0. and this will be 0 1 odd parity. This is 1 0 1 1, 1 0 is actually included in this, 1 1 is even parity. And the last 2 bits are called frame control signals. These are 2 are frame control. They will be used for only asynchronous mode only. This is going to decide the number of stop bits. This is 0 0, this is invalid. Means in case of synchronous where the stop bits are not required, probably this can use 0 0. 0 1 means one stop bit, one stop bit. 1 0 means 1.5 stop bit. So, this 1.5 periods of the clock. 1 1 is 2 stop bits. In the earlier example, you have taken 2 stop bits. This is the format of mode word register, which is the first part of control word register. And the second one is command word register. So, the last bit of command word register is transmitter ready. This is D naught bit, this is transmitter ready. Or the transmitter enable in fact. So, if this bit is equal to 1 means transmitter will be enabled, 0 means disabled. Then this is data terminal ready. 1 means data terminal ready, as I have told, data terminal will be the transmitter basically. Zero means not ready. Then we have receiver enable. This is transmitter enable, this is receiver enable. This is equal to 1 means receiver is enabled, 0 means receiver is disabled. Receiver is disabled. This is SBRK, send break characters. This is send break character. So, if this bit is 1, it means it will force the transmitter to low. If this is 0, normal operation. Then the next bit is error signal ER. This is D3, D4, error reset. So, this is equal to 1 means it will reset the error flag. So, received character can be can have error also. So, if this is 0 means it will set the error flag. Then we have RTS, IR, that enable search EH. These are the different signals D5, D6, D7. RTS, ready to send. IR, this is equal to 1, it is ready for sending, 0 means not ready. And then we have IR, internal reset. 1 means reset, 0 means set. This is also error control signal. So, again the last bit is error control. This is equal to 1 if error is, if sync pulse is detected. So, we know that in case of asynchronous transmission, we will use sync pulses, whereas in case of asynchronous, we will use start and stop bits. Thank you.